This is Rges Algebra 2, Lesson 1.7, Axioms and Properties. Now the ones above the dotted line down here are axioms for our purposes. The book actually treats the last one, substitution, as a property that can be proved from axioms, but the proof is, I think, a little obscure, and many books treat it as an axiom. So the reflexive axiom just says something like x equals x. In other words, it's going to the root. These first few are going to the idea of what does it mean to be equal. These are proper or axioms of equality. The if something is equal to itself, that goes in either direction. Symmetry says that, so talking each one of these through, the ones above the line are in red, are an expression of the axioms. The first one is reflexive. The second one is symmetry, meaning if x equals y, then y equals x, as though it were a mirror image. The third one, transitive of equality, that's what this little equal sign afterwards means. If we have the transitive property of equality, we say if x equals y and y equals z, then x equals z. What we've done is we have three statements and we're following through the argument. First step, second step, third step. So transitive means to press through or to go through. The transitive property also holds true for order, meaning greater than or less than, expressed in a greater than statement. I said if x is greater than y and y is greater than z, then x is greater than z. Again, following through the argument. There. The next one is trichotomy. For any x and y, which are real numbers, one and only one condition exists. Either x equals y, x is less than y, or x is greater than y. And finally, substitution says that if x equals z, and we have a statement x plus y, we can substitute in for the x, z. And now we have the statement z plus y. So all of these are considered axioms, fairly obvious to us, but they have to be stated in a deliberate form here so that we can then use those as tools to make proofs of other things, other principles that we use or properties that we use as we're solving equations and etc. So in the next thing below this dotted line in the blue down here, what we have is the statement of the addition property of equality. You've used this for all of your Algebra 1. That simply means that if we have an equality statement, we can add the same thing to both sides of the equation and we do not change the equality. So if x equals y, then x plus z equals y plus z. We've added the plus z to both sides of the equation, and we have not changed the equation. Similar for multiplication property of equality, we have if we have an equality, x equals y, then we can multiply the same value on both sides of the equation without changing the equality. And you know those principles or properties, but they can be proved, and they were proved in this section. So the first thing you need to do for this section is to know all of these terms on the left-hand side and how to represent them with the statements here on the right-hand side. So make sure you study that carefully. Now on the next page here, what we're going to do first is give you the answers to the quick section, Q1 through Q10. So I want you to pause and go through these quickly on your own and then check your answers and thinking with what I record here. Okay, Q1 says solve this. We know we have to solve it because it's an equation. We would add 3 to both sides and the answer would be x equals 9 plus 3, or 12. Next, we cannot solve this, so all we could do is simplify the expression. We cannot solve it because there's no equal sign, but we can combine our constants, and so -3 and -9 is -12. And that's all we can do there. Notice the difference between those two questions. For number 3, we want to commute the two factors. We have this as a factor and this as a factor. We want to change their order, so you would simply write the second factor first and the first factor second. They're not asking you, notice, to FOIL. They're just asking you to change the order. The next one is a distribution, and so I would multiply the 4x through, and I would get 4x squared plus 4 times 13 would be 52x. The next one, they're asking you, what is the additive identity? That's simply saying that if I have any number, what would I have to add to it to get that number when I'm finished? See, the identity, the same number, and the answer is 0. So 0 is the additive identity. 7% of 700. Well, you can do this a couple ways. If I were doing this on paper, I might be inclined to say 700 times 7% is the same as 7 hundredths, or 0.07. However, if I were to do, and then just multiply it out. Now, if I were to do this in my head, however, I'd go back to 1%. What is 1% of 700? And that would be pushing back the zeros as placeholders 2 times, so that would be 7. And if I want 7%, I would simply multiply 7 by 7 and get 49 as my answer. So that's the way I deal with percents when I'm doing it orally or in my head. Now the next one's an absolute value. Plug in, it says if x equals 4, so I substitute the 4 every time I see the x right here. And so 4 times 3 is 12. 12 minus 29 would be -17, but I'm taking the absolute value, so the answer there would be 17. Continuing on for the last few, they ask, is -3,000 an even number? And an even number can be either positive or negative. The only question we're really asking is it divisible by 2, and the answer is yes. For question 9, it asks, is the square root of -9 a real number? Well, recall, real numbers are composed of rational numbers and irrational numbers, but we have the real numbers, okay, and the imaginary numbers. And the difference is the imaginary numbers would be square roots of negative numbers. And that's what we have here. So this is not a real number. It is an imaginary number. Then simply adding, right in your head, you probably could all do that as 7.7. If that poses any problem at all, recall that that is the same as 3.0. Add them up, and you get 7.7. Now, I did decide to walk you through one of these proofs very carefully. They actually do the proof for you, but they're asking you to fill in the right-hand side, what would be commonly called the reason for each step. Okay, so we're asked to prove that 1 over xy equals 1 over x times 1 over y. Now, we might consider the first step a little bit of a trick, perhaps. I'm going to start with what's on the left side here, which is 1 over xy, and I'm going to multiply it by xy so that I can build an equality I know is true. Because I know that if I multiply 1 over xy times xy, I'm going to get 1, and the reason for that is the multiplicative inverse. So these are practicing some of those field axioms that you've already learned. Now, what I'm going to do now that I've got myself a true statement, and I begin with what's on the left side of the equation, I'm going to keep working steps till I can get the one on the right side instead to look like this up here. 1 over x times 1 over y. So let's see how we're going to do this. Now we're comparing from step 1 to step 2. Notice what I've done is I have introduced a multiplication. I'm multiplying on the left side and I'm multiplying on the right side. I can do that because the multiplicative property of equality that allows me to do the same thing to the left side and the right side of the equation with the multiplication operation. And why did I pick 1 over y? Of all the things I could pick, well, if you notice, the 1 over y is one of the two things I need to get on the right side. So there we have that step. Now what happened from that step to the next step? Notice I have chosen to multiply. Well, actually, what I've chosen is to take this y right here and move it outside the parenthesis. So now I've got 1 over xy times x inside the first parenthesis times y times 1 over y. So I've moved this y here out. And so I'm allowed to do that. Why? Because of the associative property. I'm rearranging the order, but I'm not moving, it to another place in my sentence. It still reads 1 over xy times x times y times 1 over y, 1 over xy times x times y times 1 over y in both statements. Same order, but the parentheses or the association has changed. So that's the associative property. Everything else is the same. Now, when I go down then to the next step, what have I changed? I've condensed this, collapsed this to a 1. So what allows me to do that? Well, that's the multiplicative inverse. Same as above. Now, when I go to the next step, I say that I've eliminated the 1. When I come down to this step, I don't have the 1 anymore. Well, what allows me to say 1 times anything is the same as that thing? That is the multiplicative identity. Notice I've gotten rid of that 1 twice. So this is the multiplicative identity axiom. And now what have I done is I go to the next step. I've introduced a new multiplier on both sides of the equation. What you do on the left side of the equation, if I multiply by something on the left side and I multiply by something on the right side, I have not changed my equality, so that is the multiplication property of equality. And why did I choose to multiply both sides by 1 over x? We'll go back and look up above at what you're trying to prove. You've already got the 1 over y on the right side, but now I need a 1 over x on the right side, so that's why I introduced that. Now what do I do in the next step? Notice I have 3 values on the left, 1 over x, y times x times 1 over x. In this step, I have 1 over xy times x times 1 over x. I have not changed the order, but I've changed the parentheses. That is the associative property. Everything on the right side is the same. Now, what have I done next? I've collapsed this to a 1. What allows me to do that? That's the multiplicative inverse. A number times or a value times its reciprocal equals 1. And what have I done to the next line? I've gotten rid of the 1. That's the multiplicative identity. 1 times anything equals the thing itself. Everything else stays the same, and the only thing I've done now to go to the very last step is notice I've reversed this order. I want the 1 over x first and the 1 over y second. I'm allowed to do that because of the commutative property of multiplication. So that's what we mean when we're saying step through the argument. I'm not going to ask you to do this, but I think it's well worth watching it a couple times to see if you can follow this very clearly.